So we'll continue with the topic, the types of digital modulation one by one. Okay. So as you can see in this block diagram, here we got a binary data bits, ones and zeros. So that is given to our encoder, and the type of encoder in here is called unipolar. Okay, so with respect to logic 1 means, so we're going to draw the waveform onto the positive voltage with the full time period of TB. Okay, whenever that you got logic 0 means for the time period of TB we have to represent 0 voltage. So this is a 0 voltage level, and here we can fix some voltages. For example, here we can fix the voltage is 1 volt. So in this manner we have converted our digital data into waveform, and this unipolar waveform will be given to a one input to a product modulator. That is original message data that we got in here, and second signal to this product modulator will be the carrier signal, which is in an analog waveform. So message is in the form of digital, whereas the carrier signal is in the form of analog. So some performance that we're going to perform, here comes the types of digital modulation. So it may be, as you can see in this diagram, it may be ASK, amplitude shift keying, frequency shift keying, and phase shift keying type of modulator that we're going to use it. As the result of it, the output will be the balanced modulated signal, and this signal will be that is called as modulated waveform. Okay, so as you can see here, the portion comes for the different types of digital modulation, and as a comparison using this diagram we'll see that. So here the first signal is the message signal, that is a digital signal which got the data, binary data as logic 1, 0, 1, 0 in a simultaneous manner. All the data bits which got a unique time period or constant time period of TB, bit duration. Okay, and as you can see, the second signal is the carrier signal. For modulation, obviously we are not going to bother or change the characteristic of the digital data or the message signal. Instead of that, the carrier signal characteristics only that we're going to vary. And as you already know, the basics of signal is the signal got three characteristics. One is amplitude, another one is frequency, and third one is called phase. Okay, so if we're going to vary amplitude of the signal with respect to the message, that is called AM. In analog communication you would have studied it. So here in ASK, amplitude shift keying, for digital modulation, what we have to do is, whenever that you got logic 1, so that same carrier signal that we're going to take and represent without changing the amplitude. Okay, so with respect to this constant amplitude value of a carrier that we're going to take and represent it for ASK for logic 1. And for logic 0, a minimum data, or else most of the cases, this diagram for logic 0, most of the cases it will be 0 voltage waveform. Okay, and as you can see, next logic 1 means the time bit duration of carrier will be taken and pasted over here, and next will be for logic 0 is most of the cases it will be 0 volt, and rarely we got a slight amplitude in here. Okay, this is called ASK. Generalized explanation for ASK. One by one we'll see in the next classes. Okay, so detailed study about all the digital modulation that we're going to see. And next one is second type of modulation, is digital modulation, is called frequency shift keying. As you can see in here, whenever that we got logic 1, the carrier pulse that we're going to take it in a constricted manner. As you can see, number of cycles has been varied in here. So from this carrier cycles, as you can see, in the number of cycles that we got in the carrier for the time period, let's say, so this is the time period for 0 to 1 second, means number of cycle counts are 1, 2, 3, 4, 5 cycles that we got. Whereas if you just look at in Bfsk for this time period of 0 to 1 second, as you can see in here, number of cycles that you got in here is 1, 2, 3, 4, 5, 6, 7 cycles that you got. So here carrier signal which got for the time period of 1 second is 5 cycles, and here as you can see we got a constricted of number of cycles. Okay, for logic 1. And logic 0 means, as you can see, it got an expanded. Okay, this is one type set of frequency and this is another set of frequencies. So that is called frequency shift keying. And if you just look at phase, logic 1, here we got the carrier signal which is added with 0 degree. So 0 degree means the same carrier that we're going to take and represent it over here for this time bit duration. And if you just take out for logic 0 means, what happened is we have to add up this carrier signal plus 180 degree. Okay, so once we added it, as you can see, the diagram has been tilted. It has been mirror image of the carrier waveform. The starting pulse starts with negative and then it goes to positive. Okay, so for this time period of instant time period, we're going to change the carrier by adding carrier plus 180 degree. So for Bpsk means we have to add up 2 degrees. One is 0 degree and 180 degree for the carrier. Okay, so this is the comparison for all the 3 types of techniques. In Bpsk we got different types of, in Psk we got different types of modulation techniques that also we're going to see. So once you take 2 degrees means that is called Bpsk, binary phase shift keying, and if you're going to use 4 degrees 0, 90 and so on means that is called quadrature phase shift keying. So one by one we will see that. So first problem related to digital communication. So this is the question that is asked in 2020. Okay, so a digital communication system transmit a block of n bits. So a block of n bits, so up 1 zeros and this manner for n number of bits that it got. Okay, so in a block it got n number of bits and the probability of error. So what is probability of error at decoding means? So at transmitter, here we got this block. So if you take a communication, we got 3 main components for a communication system. So one is the transmitter, and then we got a channel, and then that data will be received. Okay, so as you can see in channel only noise will get to added. Okay, so in channel noise will get to added. So this is the receiver. Okay. So our transmitter, here we got an n number of bits that is modulated and that we're going to transmit using the channel. At the receiver side, we have to demodulate it, we have to decode it. Okay, so let's say the transmitted data is 1010. Okay, 4 bits that we got. After it is traveled wirelessly and it is reached to the receiver, the data received is 1110. As you can see, a second bit has been varied in here. So that will be calculated using probability of error. So the probability of error in decoding bits is alpha. The probability of error, chances of getting error is that we're going to take it as alpha. The error event of each bit is depend on error event of the other bits. The received block is declared errorless. Okay. So if at least one of its bit is decoded wrongly, the probability that the received block is errorless. So on the formula to calculate errorless is, as you can see in here, y is the received data. Probability of no error can be written as 1 minus alpha. Okay, so if the data is n times means you have to introduce the power of 1 minus alpha of n. Okay, so this is the formula to calculate for n number of block for probability of error. Okay, so as you can see, the answer will be C within the given options. 1 minus alpha to the power n number of times. So this is the problem, generalized problem that is related to digital communication that have been asked. And the topics that we're going to see related to digital communication or digital modulation are, so one is ASK, Bfsk, Bpsk, Dpsk, Qpsk, MRAPSK, QAM, and finally apart from the digital modulation, one more topic that is called source coding. Okay, so first we'll see amplitude shift keying, what is called ASK, in a detailed manner. So the first topic in here is amplitude shift keying. So as you can see in here, the first data is binary data, logic 1 zeros 1 zeros. So next step what we have to do is we have converted using an encoder of unipolar. Here we have changed the binary data into waveform. For the time period for all the binary bits is TB. Okay, and second signal that we got in here is the carrier signal, that is an analog in nature. So, and as a result of what we have to do is to generate ASK waveform whenever that we got logic 1. So this is the logic 1. So the same carrier that we have to take for the bit duration of TB, and we have to represent it. Okay, and for logic 0, so as you can see in here, there is no pulses. So that's why it is called on off keying. Another name for ASK is OOK, on off keying. Okay, so in this manner, for the rest of the bits, we can vary the characteristic of a carrier waveform. So this is called ASK. So binary message signal is also known as baseband signal. And the equation for the ASK is, as you can see in here, after this waveform, modulated waveform, in terms of equation that we have to represent it, equation is A into cos omega ct or omega t, that we can represent. Here we got 0. Okay, so this equations, once you combine it, the modulated waveform S of t, that we can rewrite it as A into cos omega is 2 pi f, and for represent omega ct means you can represent the equation term as 2 pi fct. So this is for logic 1. And logic 0 is, as you can see, both the values are 0. So rest will be 0 for binary. Data is 0. And equations that we have for A is the amplitude representation in terms of E, energy. Okay, so as you can see in here, P is equal to A square by 2, and that we can represent amplitude in terms of energy. Equation will be A is equal to root 2 E by TV. Okay. So, and important formulas that we have to study, not only for ASK, for all the types of digital modulations, are probability of error, and probability error for coherent ASK and non-coherent ASKs are the equations that is given in this tabular column. Okay. So, and apart from that, we got a constellation diagram representation for ASK. So here we have used two data. Okay, it's logic 1s and logic 0s and corresponding equations. So this is the constellation diagram point for logic 1. Okay, so and here, as you can see, the point S2 is for the logic 0. So S1 and S2 that we have to represent, and the distance between those 2 points also will be calculated using D12 is equal to root 2 EB. So probability of error equations, as you can see in here, the constellation diagram. So this is for 0, and as you can see, this is for logic 1. And bandwidth equations for ASK are B by BT. Okay, so what is bandwidth? As you can see in here, twice into bit rate. That also that you can study. And advantages is it is very simple to design, and disadvantages, because of the simplification, there is a lot of chances of noise. Okay, so immunity towards noise is very poor in ASK system, and also it requires a synchronization operation. What is synchronization means? For encoder, whatever the type of carrier that we are using, that exact carrier that we have to use for the demodulation side. That's why it's called a synchronous coherent detector. The same carrier that we have to use at the detector side, demodulation side. That's why it is called a coherent detector. And this is the tabular column for all the types of modulation in a digital, and its bit array calculation equations, and the important formulas related to digital signals, probability of error for all the types ASK, FSK, PSK, and Bfsk. So this is a whole tabular column comparison for all the types of ASK, FSK, and PSK, and its related equations, along with its important points that you should have to aware, okay, to solve the problems. And now we'll see the next topic apart from ASK. Second topic is binary phase shift keying. Got logic binary data bits. Okay, so logic 1, logic 0, in this manner we got a binary sequence data, and that we have converted and draw in terms of waveform structure. Okay, so for modulation, obviously to a modulator block, one input should be a binary digital data and second input should be the carrier, so that we can get the modulated data. Okay, so here we are going to use the modulator name, which is called Bfsk. Okay, so one input to this block is the binary data, input message signal, and second input should be the carrier, which is in the form of analog, which is in a continuous signal. So here your message is in digital and the carrier is in the form of analog. Okay, so now we'll see the modulation waveform, because based on this only we're going to see the problem. As you can see, for Fsk, logic 1 means the same carrier frequency that you have to take and represent it. So here you got 2 cycles. So, and here also for logic 1 you got the same cycles. Okay, so whereas for logic 0 you have to change. If number of cycles are different, varying means, that means your frequencies vary. Let's say this here we got 2 cycles, which means you got, for example, 2 hertz, that you can name it out. Instead of that time, so here we'll take for 1 second of time period, here we got 10 number of cycles, means you got 10 hertz. So number of cycles are increases means frequencies also will get to increase. So here for logic 0 you got different frequency. Okay, so for logic 1 you got a different frequency. So our aim is for logic 1 and logic 0 you have to use 2 different carriers. So that is the concept that you should have known. And logic 1 carrier frequency is called mark frequency and logic 0 frequency is called space frequency. So these 2 points that you can remember. And also in last class we have seen the theoretical formulas related to it. So for logic 1 means you have to use a separate frequency and logic 0 means you have to use a separate signal. Okay, so as you can see, logic 0 we got different frequency, number of cycles are in a very extended manner, that is a different frequency, and to the logic period of TB, here you got different frequency. So that's the point, it differs in here. And the energy for the signal you have to represent with EB. Okay, and what is delta F is, that is called deviation. Deviation means, as you can see, here we got a elongated waveform, here you got a very congested waveform, right? So which means here imagine, so this is the frequency, that is the rubber band in an ideal position. Once you give the force to rubber band, you can actually see the oscillation, which means instead of getting the ideal shape of the rubber band, you got multiple shapes, right? So that is called the different frequencies. So in between actual waveform, if I'm going to zoom this frequency means you will get multiple oscillations. Okay, so that is called deviation, frequency deviation, that is called delta F. And very important point, both the signals are in a orthogonal. In last class itself I have told you, orthogonal means even though we have using 2 different frequency and we're going to transmit in the same channel, means both signal have to be orthogonal, and the property is integral with the time period of 0 to TB, S1 into S2 is equal to 0. It's very important orthogonal property. Okay. So, and signal space means, again we got 2 data and how those 2 data equally spaced. Okay, that is called signal, literally the name implies signal spacing. And logic 1 will be placed in phi 1 of t place and phi 2 of t will be placed in here. Okay, sorry, not this, you are not supposed to place the data in there. Just a minute, I'll erase it. So the constellation diagram for Bfsk will be just like this. Okay, so this will be the constellation diagram. X-axis is for pi 1 of t and y-axis is called phi 2 of t. So logic 1 will be placed in phi 1 of t. So this is the energy into cos, and logic 2 0, that is called, it have to be placed in phi 2 of t. So this is the simple constellation diagram. So with the distance d we have placed it. Okay. So as you can see in the region, this is the boundary region which separates logic 1 and logic 0. Okay. So and the probability of error, that also we have to calculate. So this is the same formula that is used for ASK as well, for Bfsk and ASK error probability. So if you are going to transmit the data, let's say if noise is added and the data is some spacedly it has been placed, means that is called error, that we have to calculate. So dependence of error probability, the distance between two signals points, can be calculated using this formula. Okay, and this problem in last class itself we have covered it. Okay, so in today's class we're going to see a new problem which is related to Fsk. So this problem also we have covered. So now we'll see 2014. There are actually 4 set of question papers at the year of 2014. Communication system related question they have asked in set 2. Okay, so that is in particularly digital modulation they've asked in this year. Okay, so in 2014, I'll read out the question. So coherent orthogonal, the name itself starts with orthogonal. Orthogonal means in the same channel. Here they have given AWGN channel. In the same channel, so this side is transmitter and here we got receiver. In the same channel we can transmit 2 different frequency, because Fsk is the concept of using carrier of 2 different carriers, right? So as you can see, which is an orthogonal property, integration of 2 signals S1 of t and S2 of t should equal to 0 at the time limit 0 to TB. Keep that the point in mind. Okay, so I'll read out the question once again. So here orthogonal binary Fsk, which is equally probable, and as you can see here we got first frequency and second frequency S1 of t and S2 of t, with power energy that they have given it as amplitude value is given in here as alpha is equal to 4 MV. For both signal amplitude value is 4 millivolt. Okay, as you can see, assume AWGN channel. AWGN channel means additive white Gaussian channel. Noise will be added along with the data, along with the original signal. That's why it is called additive in nature. So and the type of channel that we're going to use is called AWGN. So with two-sided noise power. So for both the data, both signals, we got a power spectral density as N0 by 2 and the value is also given. And optimal receive, using an optimal relation, again the question completes just like this. So to a receiver, the characteristic equation can be defined with this. Okay, and the bit probability error data RB is also given, data rate is also given, that is 500 kbps. Okay, so out of this we have to say which is the characteristic. Once we solved it, we have to know which type of option is the correct answer, probability value that we got in here. Actually they are asking bit B is equal to what they are asking. So in a normal channel, if I am not taking AWGN, in a normal case, how does a Bpsk data with one transmitter and one receiver, how you can transmit and receive the data in AWGN channel means, I'll tell you, just a minute. Okay. Okay, fine. So okay. So here we'll pick out the data and first write it. So answer is option C. We'll see that now how. So there are 2 equal probable symbols are given. So in question they have given 2 equation. We'll take those 2 equation. I'll write it now. So here its symbol is changed. So it is S1 of t and this is S2 of t. Those 2 signals that we have taken and written in here. Okay. So next step what you have to do is, alpha is also given. The given data are, we are going to pick it and write it. Alpha is also given. Similarly is 10 to the power minus 3 volt. Okay. So next step, as you can see, data rate is also given. So if you read out the last question, last point, data rate RB is also given. From that we can get TB. So RB is equal to 1 by TB. Okay, so that is 500 kbps, that is 5 into 10 to the power 5 bits per second. And noise spectral density is also given in the data. So noise spectral density formula is N0 by 2. Just take and multiply 2 with this equation. So you'll get to 10 to the power minus 12. Okay, so now we have to calculate bit energy, and the formula is amplitude power A square or alpha square into T divided by 2. So in here T is not given in the question. Instead of T we got R. So how R and T is related, means just now only I have told you RB is equal to 1 by TB or 1 by T, a single bit duration. Okay, so then you can directly substitute the value and you will get the value for EB. So finally we have to get the error probability value. So error probability equation also I have showed you. So probability of error is Q of root EB by N0. We already know from the given data we have calculated N0 value, and using the energy bit formula also we have calculated EB value. So directly substituted you will get the, so the powers will be cancelled out. So only you got a root to the power 16. Once you take the root out, the answer will be Q. So now we have find, so answer will be D in here. Okay, so for the given question, C in here. For the given question, the correct answer is C. So in 2014, they have asked you. So now we'll see again based on Bfsk, we'll see the question that is asked in 2002. Okay. So for a bit rate 8 kbps, the best possible values of the transmitted frequencies in a coherent binary Bfsk system. So what is coherent means? It have to be matched. So there should be a synchronization between the carriers at the transmitter and receiver side as well. If the carrier is matched on both transmitter and receiver side, those those system is called coherent. Okay, so here we are going to use a synchronized carrier, that is coherent binary Bfsk system that we are going to use in here. And next, so out of this option, for 8 bit rate, so for the kbps of 8 kbps, we have to calculate which are the frequencies are related to Bfsk in the following. So for this important point that you should have to remember, for all the Bfsks and all the digital modulation, the data will be should be in an integral multiple times. Okay, so here as you can see, the transmitter frequency in coherent Bfsk should be integral of 8 bit. So as you can see here, you got kbps, and which is equivalent to 8. So as you can see, Bfsk is the possible value should be 8 kbps integral multiples of bit rate. Okay, so which means 8 kbps equal to 8 kilohertz. It should be integral multiple. As you can see, the values should be like 8, 8, 16, 24, 32, 40. So in this given option, you should have to remember. So key to this question is integer multiples. Okay, so from this, as you can see, 16 is there in option A, 16 is there, 20 is not. So this should be the integral multiples, right? So answer will not be A. And similarly, if you take B option in here, we got 32, but 20 is not there. So B will not be the correct answer. If we just look at the C, we got answer should be here is 24. I have typed it wrongly. Okay, so it will be 24 is also there, 40 is also there. So the correct answer will be C in here. Sorry, just a minute. Here I have made it wrong. So the answer is option D. Okay, so correct answer is option D. As you can see, 32 is there, 40 is there. So the correct answer is D in here. So for this given question, so twicely they have asked question like this. So you have to take the given values and it have to be integral multiples. 8 times you have to multiply it, and in the option you have to check the correct answer. Okay. So as a continuity relates to the same problem, we'll see one more that is asked in 2020 and carries 2 marks. Okay, in a digital communication system, employing frequency Fsk, 0 and 1 bit are represented by sine wave. 0 is for 10 kilohertz, 1 bit is for 25 kilohertz respectively. The waveforms are orthogonal. So okay, so so the waveform is orthogonal. Again, take the value integer multiples. Okay, so here we got two frequency, 10 kilohertz, 25 kilohertz. In previously we got only one frequency, that is 8 kbps. Here we got two frequencies. So for that you can take a bitrate value and take HCF. So common value that we have to take. So while taking HCF, you got a common value is 5 kilohertz. Okay, so from this we can say, or else in a simpler way, 5 kilohertz, once you got the value, substituted with TB is equal to 1 by RB, that is equal to 1 by 5K. So once you divide it, the correct answer will be option B. Or else another method to solve this question is 0 bit is for 10 kilohertz, right? So we can take TB0 is equal to 1 by 10K. So that is equal to 100 milliseconds. Okay, and for similarly logic 1 representation is 25 kilohertz, which means TB1 is equal to 1 by 1 minute. Okay, TB0 is 100 milliseconds. So from that RB we have got 100 milliseconds, right? So again, if you're going to write in terms of integer multiple, means you will get 200 microseconds and then 300 milliseconds, and it goes on. Okay, so for TB1 again write the integer values, that is 80, 40 times you have to multiply. So 80, 120 and then 160 and then 200. Okay, so in between you have to check which number is common. So as you can see, 200 is common, so you can take that and write it. So it is also another method that you can solve it. Okay, so Bfsk is over. Now we'll see Bpsk. So we'll first see the generalized formulas related to Bpsk and then we'll continue. Okay, just a minute. So to get the concept for Bpsk, you should know what is meant by phase. For a carrier wave, let me clear you the concept for phase in here. So here we just taken a single waveform. Okay, a single cycle that we have taken, a sinusoidal wave. So it has been spaced, as you can see, 0 degree, 90 degree, 180 degree, 270 degree, again 360 degree in here. So in betweenly we got phases. So what is phase? As you already know, height is called amplitude. The whole periodic time with respect to second time is called frequency. And what is phase means, as you can see, so it is a one type dimensional view. So for a normal sine wave. So if I want to rotate it with a multi-dimension, mean, as you can see, this is how the waveform looks. So it actually rotates in a 3-dimensional. If you're going to take a sine waveform, means it will be in this manner. Okay, in a circular manner it will tend to rotate. So as you can see, now we have through that screen that you are viewing. So it is onto your screen view and it is the diagonal view. As you can see, for this is called phasor diagram. So with respect to this rotation, we got different phases. So at different angles. So as you can see, 360, 0 and then 90 degree and then 180 degree, and then it continues to change the phases. If I'm going to freeze it, you can actually see. So along with it, this is a 30 degree, 60 degree, 90 degree waveform. At the origin, if the waveform is moved towards the center axis, that is called 90 degree waveform signal. Okay, that is equivalent to sine theta plus 90 cos waveform. Okay, so I'll tell you what is phase shift means. As you can see, the red diagram and blue are the first origin which starts at the 0 axis. And as you can see, blue is in the original space, but in terms of 90 degree, sine theta plus 90 degree, which will be cos waveform. So cos will originate at this 90 degree origin. Okay, so and this is the 90 degree phase shift. And 180 means, as you can see in here, so this is 0 degree waveform and it is approximately 60 degree, and then here we got 270 degree. So in this manner we can phase shift it. So in Bpsk, what is the concept that we're going to use is, we're going to use only 2 degrees. Logic 1 means you have to add up 0 degree for the carrier, and logic 0 means you have to add up 180 degree along with the carrier. Okay, as you can see in a Bpsk, here we got the carrier signal. So this is the original carrier signal, which consists of amplitude and cos nature along with the frequency. Okay, so as you know what is that amplitude in terms of power. P is equal to 1 by 2 A square. Okay, so for symbol logic 1 means you have to add up 90 degree along with the carrier, sorry 0 degree along with the carrier. So you'll get the same carrier frequency for logic 1. And logic 0 means you have to add up 180 degree. So 0 degree waveform, how it will looks, 180 how it looks, I'll show you. As you can see in here, B of t ranges with voltages, logic 1 and logic 0. So if I'm going to add up logic 1 means I'm going to add up carrier with 0 degree. So this is the 0 degree waveform, which starts at the origin of 0. This is the one cycle that I have taken and explained it. And for logic 0, you have to add up 180. 180 is this origin point. It have to start from this onwards. Okay. So normal waveform and its mirror of a sine wave. As you can see in this waveform, we got two bits. Logic 1 means you got a normal carrier, and that you have to take and represent it. And logic 0 means you got an inverted carrier. So the same carrier that you have to take and inversely you have to draw. So this is called Bpsk. In Bfsk means logic 1 and logic 0 we have used two different frequencies. For phase we are going to use a single carrier, but the phase will going to vary. That is called Bpsk, binary phase shift keying. Okay, and the formulas related to it. As you can see, it differs. Okay, so energy bit is different for both the data. Here we got plus 0 degree. Here we got plus 180 degree. So as you can see in here. And the constellation diagram, this is how it will be equally placed. And the difference, if you're going to calculate it, the distance between those 2 points is, you can take it by root EB minus root EB. So which will give you the distance value is 2 root EB. Okay, so distance between those 2 points is called 2 root EB. And the center boundary which make a space in between those two values is the decision boundary in here. Okay. So and power spectrum, the power probability of error will get to vary in here. So value will be 2 EB in here. So in Bpsk and Bfsk we got EB by 2 N0. So here it will differ for Bpsk. Okay. So as you can see the constellation diagram and the energy waveform for it. So it is the slide which shows you the three different types of energy probability of errors for three different digital modulation for ASK, FSK, Bfsk. Okay. So now we'll solve the problem related to Bpsk. So in 2014 at set 1 they have asked the question. So in a normal system, what is this concept? The question it says is, so here in the diagram they have given a system. So here the input will be 0 and 1. So you're going to give input to this modulator, to a Bpsk modulator, logic 0 and logic 1. At the end also we're going to use, at the receiver side we're going to use a, so this is the transmitter side. Okay, till here we got a transmitter, and till from here to here it is the receiver. So obviously using a demodulator you have to extract the original data bits, logic 0 and logic 1. Okay, so in betweenly we got a channel. So if you just closely look at it, we got two different channels. Okay, so both the channels are additive. Okay, so now we'll read out a normal Bpsk system. We got error, the probability of a bit error rate function is Q of root gamma. Root gamma is signal power divided by noise power. Okay, so that is EB by N0 you can say. Over a AW channel with a two-sided N0 by 2. So the nature of the PSD AWGN channel is N0 by 2. Okay, so a system with two independent and identical AWGN channels with noise power spectral density N0 by 2 is shown. The Bpsk modulator receives the sum of output or both same. Okay, so our aim is to actual system equation will be just like this. For a common channel, for a common and single AWGN channel, the bit error rate formula will be, so I'll show it. So bit error rate formula for a normal transmitter and a single AWGN common channel and then receiver. So bit error rate equation will be Q of root gamma, that is given in the question. But for the actual question, the bit error rate is shown in here, and we have to calculate value for B. So how, that we'll see now. Okay. So as you can see from the given data, we have taken Bfsk, means using the constellation diagram. Here we have marked it. Okay, AWGN channel. So as you can see in here, just look at this diagram carefully. It is the modulated data, that is the signal that we're going to take it as X. Once it is splitted, and here we're going to write it that into, because in the channel AWGN channel 1 noise will be added. So additive nature, that's why you are adding it with X plus N1. And here you got X plus N2, this noise will be added. As a result, you got 2X plus N plus 1. Okay, so here we got 2X plus N plus 1. And for a simpler sake, we can write separately write signal, original signal and noise signal as separate. So original signal will be in terms of X to the power 1, that we're going to write, N1 plus N2, that we're going to write it as a common noise. And bit error rate formula we already know, 2 into E by N naught, right? So here in terms of this is the signal, means for that you have to write the energy. So we can write it as E1 divided by N, and its noise PSD is N naught power 1. So as you can see, amplitude signal is get twicely increased, which means you can write energy as not 2E, you have to write with 4E. And even if you're going to vary the amplitude for the noise twicely, means the noise will not get to change. Noise characteristic will not change. Okay, so you can write it as N naught. So as the result, you can change this equation just like root 4E by N naught. And after that, you just take out the root commonly. So you'll get root 2 values by separately writing it. So 4 can be written it as root 2 into root 2. We'll take root 2 commonly outside. As a result, here we have kept the original formula, original power probability of error, bit error rate formula. Okay, so apart from this gamma value, once you compare this equation and question given equation, we can actually get B is equal to root 2. Okay, so that's the answer for it. So that's it.